Hello everyone. In this video, I will walk you through how I built and improved my diabetes prediction model, how I evaluated whether it was overfitting or underfitting, and how I would deploy and monitor it in a real healthcare setting. So apparently this is a binary classification task, predicting whether a patient has pre-diabetes or diabetes. In a healthcare context, prediction errors are not equal. If we miss a diabetic patient, that's a false negative. The consequences can be serious. It may delay diagnosis and increase the risk of complications. If we incorrectly flag a healthy patient, that's a false positive. It may lead to unnecessary screening and additional costs. Because of this imbalance, in consequence, I treated this as a cost-sensitive problem, not just a simple accuracy optimization task. I started with basic EDA. First, I checked for missing values in both the training and the test sets. Then I examined duplicates in two different ways. Duplicates across the full row, including the target. Duplicates across features only. I removed exact duplicates from the training data. The reason is that duplicates can artificially inflate validation performance. If the same record appears multiple times, the model may memorize patterns instead of generalizing. Next, I looked at the class distribution. The positive class, diabetes, is significantly smaller than the negative class. Because of this imbalance, accuracy is misleading. So instead, I focused on F1 score and ROC AUC. F1 balances precision and recall, which is important when missing positive cases is costly. ROC AUC measures how well the model separates the two classes across thresholds. For pre-processing, I used the standard scalar for linear models and the neural networks. I implemented scaling inside a pipeline to prevent data leakage. I also used PCA, but only for visualization. When I plotted the 2D PCA projection, I saw that the two classes heavily overlap. That's just the problem is not linearly separable. So this gives me early intuition that nonlinear models like tree-based ensembles will likely perform better than simple logistic regression. Importantly, PCA was not used for final training, only for understanding the data structure. I compared several model families. First, logistic regression with L1, L2, and elastinic regression, and also with class weight balanced. Logistic regression is interpretable and stable, but it assumes a linear boundary. Second, tree-based models, random forest, actual trees, balanced random forest. Tree models capture nonlinear interactions automatically. However, their probability outputs are often poorly calibrated. So I use calibrated classifier CV with sigmoid collaboration to improve probability reliability. This is especially important because I later turned decision thresholds. Third, I trained hist gradient boosting, which ultimately performed the best. Boosting works very well on Tableau data because it sequentially corrects errors and captures complex feature injections. To handle class imbalances, I tested three main strategies. Smooth class weighting balanced ensemble variance. Smooth improved recall by sometimes increased false positives. Class weighting was more stable, but the biggest improvement didn't come from resampling. It came from threshold turning. Instead of using the default threshold of 0.5, I searched the thresholds from 0.01 and to 0.99. I optimized both F1 score and a custom cost function. In my healthcare cost setup, false negatives were assigned a much higher cost than false positives. I compute total expected cost from confusion matrix counts. This reframes classification as a decision policy problem, not just a modeling problem. To evaluate model fit, I plotted learning curves using stratified cross-validation. At small training size, the training F1 was much higher than validation F1, indicating clear overfitting. However, as the training size increased, the gap between training and validation scores narrowed. The curves stabilized. The difference converged to around 0.02 to 0.03. This suggests mild overfitting at small sample size, but acceptable generalization once enough data is used. Because the gap is small and stable at larger size, I conclude that the final model is reasonably well fitted. I also computed the formulation feature importance using ROC-AUC scoring. This helps identify which health indicators contribute most to diabetes prediction. All we can find is the gem health. Permutation importance is model agnostic and reflects actual predictive contribution rather than internal model structure. If deployed in a healthcare setting, I would monitor feature distribution drift, prediction score drift, changes in diabetes prevalence. If drift is detected, I would retrain the model, recalibrate probabilities, return the decision threshold. Because healthcare data evolves over time, monitoring is essential to maintain performance. To summarize, performance improvements came from careful data cleaning, proper imbalance handling, nonlinear model selection, probability calibration, threshold optimization, learning curves analysis. Most importantly, I approached this not just as a classification task, but as a real-world decision support system. Thank you.